In the last chapter, we talked about what a rational function was, and then we solved them. A rational function is a function or a polynomial that has a variable in the denominator. And so we're going to see rational functions today. We're going to talk about graphing them. And just like everything that we've done, our calculators are going to be a really good tool to use, okay? And we're definitely going to use our calculator to help us here. But there's going to be some things that we're going to find by hand to kind of help us with guiding and knowing where the graph's going to be. The hard thing about today's lesson or these types of graphs is every single one of them is going to be just a little bit different. When we look at like a quadratic equation, we know it's a parabola, and we know what it's going to look like before we ever put it into our calculator. Maybe it opens up, maybe it opens down, but it's still a parabola. When it's a cubic function, we know that it's the snake-like graph of some kind. A linear graph is always a line of some kind. But when we have a rational function, all of these are going to have a little bit different look to them. So I'm going to give you some different examples of some of the different kinds that we're going to see. But before we get into that, we're going to talk about some of the things that we're going to find. And you might remember a little bit of this from Algebra 2, because we've done some of these things before. But a rational function is where you essentially have a polynomial divided by another polynomial. And the one thing that we've talked about a lot in this semester is whatever's on bottom, whatever polynomial is on bottom, we can't let that equal zero. We can't have zero on the bottom of a fraction, ever, okay? And so there's going to be a lot of things today that would give us that, and we're going to have to determine like what those values would be. Okay, I'm going to kind of go through some of the different things that we're going to be looking for today, and then we're going to do some examples of all of these. All right, so first one that we're going to talk about is a vertical asymptote or a hole, okay? And those kind of go hand in hand. That's why I'm doing them together. They both are based off of the denominator, okay? So a vertical asymptote is a vertical line that the graph is going to approach and get really close to but never cross or touch. And we've seen them before. We've seen asymptotes. These graphs, in a lot of cases, are going to have a vertical asymptote, and eventually we'll talk about the horizontal asymptote as well. The one thing we really haven't seen much before is the hole. The hole is going to be kind of a little bit different, and there won't be very many graphs that have a hole, but there will be a few that do, and so we got to talk about how can we find that hole. And one of the hard things about the hole is your graphing calculator will not show you that hole. It'll be like a hole, a gap in the graph, or a hole in the graph, and we got to know where that's at, and we got to be able to find that hole, because the calculator's not going to be able to do that for us. So to find a vertical asymptote, we're going to always set the denominator equal to 0. And it might be just like x plus 2, setting x plus 2 equals 0, if that's what my denominator is. It might be as simple as that. It could be a quadratic equation where I have to maybe factor it first, set it equal to 0, and then find out what my vertical asymptote is going to be. If I have a hole is going to have a common factor on top and bottom. And so what that means is maybe I have like an x plus 3 on top, and I have an x plus 3 on bottom. If they have that common factor on top and bottom, then there would be a hole at that common factor, whatever that common factor is going to be. I would set it equal to 0 and find out what that hole is going to be. So that's going to be the first thing that we're going to look for today. Does it have a vertical asymptote? Does it have a hole? Okay. And I'm going to kind of list these out. That'll be the first thing we're going to look for. The second thing we're going to look for is a horizontal asymptote. Okay, this one's a little bit harder because there's essentially three different rules that we have to know to determine what our horizontal asymptote is going to be. It's all based off of the degree. Okay, we're going to look at the degree of the polynomials because we're going to usually have a polynomial on top, a polynomial on bottom, and we're going to compare the two degrees of those two polynomials. Okay, so the first, if the top is bigger than the bottom. If the top is bigger than the bottom, that would be something like x squared minus 4 over x minus 3. Okay. If the top is bigger than the bottom, then there is no, and I'm going to abbreviate here, no horizontal asymptote. So I'm looking at the degree. Here the degree is 2. Down here the degree is 1. So 2 is bigger than 1. We're only looking at the degree. And so there would be no horizontal asymptote. Okay, the second one we're going to look at, if the top is less than the bottom. Okay, if the top is less than the bottom, it could be just the opposite of what we just saw. Maybe I have x minus 3 on top and x squared minus 4 on bottom. Now the degree on top is 1, the degree on bottom is 2. And so in this one, the horizontal asymptote is y equals 0, okay, which is otherwise known as the x-axis. So the x-axis is the line that it's going to approach and get really close to. And then the third, what happens if the top is equal to the bottom? So here the degree on top is 2, the degree on bottom is 2, so the degrees are the same on top and bottom. So the top is equal to the bottom. And we're going to take the two leading coefficients. In this case, they're both 1. Sometimes we may have another leading coefficient there, but 1's probably the most common one that we're going to see. And we're going to divide the two leading coefficients. I'm just going to make a note here so that if you look back at your notes, then you know what number we're dividing the two leading coefficients. So those are your three possibilities, okay? And so horizontal asymptotes are a little bit harder to determine, but you'll kind of get the feel for it as we go. All we got to do is look at the degree, and you're not going to have all three, right? You're going to have one of the three, and we just got to decide which one does it fit under. Okay? And it's all based on comparing the top and the bottom. Okay, the other two things, we're going to find the vertical asymptote or a hole. We're going to find the horizontal asymptote. We're going to see if it has any x-intercepts. We're going to determine if the graph crosses the x-axis. Some graphs will, some graphs won't. That's one thing that we've focused on a lot throughout this chapter, right? Where does it cross the x-axis? What are my zeros? And in order to do this, we're going to set the numerator equal to 0. The numerator is the top of your fraction. So whatever polynomial I have on top, we're going to set that equal to 0, and that'll tell us where does it cross the x-axis at. And then we're going to find some y-intercepts. And to find the y-intercept, we simply plug in 0 for my x. We did that the other day when we graphed polynomials. And we said, okay, let's plug in 0 for my x value. Let's find out what the y value is. Once again, it may not have a y-intercept. It may not have either one of these. But if it does, we want to find out where it is. And both of those, we can usually use our calculator to help us find those as well. Okay, so the calculator could be a pretty good help on both of those also. The calculator, as far as the horizontal and vertical asymptotes go, we can kind of visualize it, but the bad thing about the calculator is it's not going to actually put that line or that asymptote into your calculator, so you're going to have to kind of visualize about where that would be based on the function that I have. Okay. Once we have these 4 things, these are the 4 things that we're going to try to determine on everyone that we graph today. And that's going to be the majority of our homework today is they're going to give us a rational function, and we're going to find all of these pieces of information, and then we're going to try to determine what the graph is going to look like. Okay, there will be some problems where we're just doing, like, what is the vertical asymptote? What is the horizontal asymptote? Where we're not necessarily graphing it, but we will do a lot of graphing today. So the examples that I'm going to give you are just going to be some graphs of some of these rational functions and try and show you some different possibilities that we might have. And the top is less than the bottom, means y equals 0 is my horizontal asymptote. It's just y equals 0. That's probably going to be your most. If I go back. All right, so here we go. F of x equals 1 over x minus 3. Some of them are going to be a lot more in depth and have a lot more, okay? And you might say, well, I thought we had a polynomial on top and bottom. This is a polynomial. It doesn't look like a polynomial because it doesn't have any x's on it, right? But it's just a number, right? And a number is a constant, and a constant is a type of polynomial. It's just a polynomial with no variables attached. On bottom, we have a linear function, okay? So we're going to go through all of the things that we just talked about, try to determine what do we have here, and then we're going to graph this. Okay, and I'm totally okay with abbreviations here because we're going to talk about vertical asymptotes and horizontal asymptotes a lot. So I'm just going to use VA. We do x minus 3 equals 0. So x equals 3 is my vertical asymptote. Okay. There is no hole here. Okay, you're not going to have holes very often. In order for this to have a hole, I'd have to have x minus 3 on top and x minus 3 on bottom, and we don't have any factors on top. So there's obviously no hole here. Okay, horizontal asymptote, this is where we're going to use that rule we talked about just a second ago. What would be the degree of the top here? What do you guys think? Okay. If there's no variable, then my degree would be 0. Okay, so no variable means no degree. So my degree is 0. On bottom, my exponent assumed here would be 1. So 0 and 1 are my 2 degrees. So the top is less than the bottom. Just remember that that's your x-axis. Okay, x-intercept is none. Because the polynomial that we have here doesn't have a variable attached, right? I can't set 1 equal to 0. If I set 1 equals 0, then we couldn't solve it, right? It has to have a variable in order to solve it. So there is no x-intercept here. It will not cross the x-axis. And then the y-intercept, we're just going to plug 0 in for x, and we're going to find out what y is. So 1 divided by 0 minus 3 would be negative 3. So 1 over negative 3, or negative 1/3, is my y-intercept. Okay, and we are going to use our calculator here, but before we use our calculator, what I like to do is I like to put all of this on the graph first, and then that kind of helps us to kind of guide where our graph's going to go based on everything that we've got here. Okay, the vertical asymptote is x equals 3. The horizontal asymptote, we said, was y equals 0, which is the x-axis. So you don't necessarily have to redraw a line on top of the x-axis, but I'm doing that here just to show you that the x-axis is the line that it's approaching. It does not have an x-intercept. The y-axis at negative 1/3. And that's just kind of an estimate, somewhere between 0 and negative 1. Okay, so now we're going to put this into our calculator, and we're going to try to determine what the graph looks like based on all of the things that we've determined. And on these graphs, I'm not asking you to make like a table of values. So we don't even need to go to the table in our calculator and get specific points. We could, right? It gives you a table, right? But we're just doing a basic sketch based on all the things that we found. One of the things that I would point out too, come back to this example right here, and this is the easiest one to talk about it. If I asked you what the domain of this graph is going to be, there's going to be a few questions today about domain, okay? And once again, we know that domain always goes back to our x values, right? And so here we're going to say x cannot be 3. And that's okay. You can write x cannot be 3. If they ever ask us to write it in interval notation, then the way we would say that is negative infinity to 3, and then 3 to infinity. We're just taking 3 out of it. Okay, so just another little piece that you might see today that I forgot to talk about when we were doing that. But that would be the easiest one. And you could do it for any of those graphs. All right, the next one looks like this. A little bit more in depth than the one we did just a second ago. We have an actual polynomial on top and bottom here. Both of them are quadratics. And so what we would want to do in this situation first is we really would rather have it in factored form, because that's going to be easier to kind of determine all the things that we want to determine based off of what we have. And so you don't necessarily want to solve it. Factoring it would be enough, and we will solve it eventually. But if I wanted to factor x squared minus 1, what would x squared minus 1 factor into? What method could we do there? Kind of. It is perfect squares. And we sometimes forget that 1 is a perfect square. There is no GCF, so we can't take a GCF out. Yeah, difference of perfect squares. You got it. DUPS. X plus 1, x minus 1. Okay, on bottom, we have a trinomial. We want to factor the trinomial. Because there's no number in front of x squared, we're going to do the product and the sum. So what multiplies to get -6 and adds to get 1? The middle number would be 1. Okay. -2 and 3. Okay, now order doesn't really matter which one you put first or which one you put second. Okay, once again, there's no hole, and there's no hole because the factors on top and the factors on bottom are different. If I had an x plus 1 here and an x plus 1 here, then I'd have a hole at x equals -1. I'll show you one that has a hole here in just a second, but this one has no holes. My vertical asymptote, this time I'm going to have 2 of them because I have 2 factors on bottom. I have x plus 3 and I have x minus 2. If you want to set it equal to 0 and solve it, you can, but I mean, these are just one-step equations, so it's pretty straightforward. X equals -3 and x equals 2 would be my 2 vertical asymptotes, just setting the denominator equal to 0. So that's the big difference here, is this one's going to have 2 vertical asymptotes instead of 1. I told you all these graphs are going to look a little bit different based on the polynomials that were given. Okay, horizontal asymptote. Degree is 2, the degree is 2. So top and bottom are equal to one another. And what we talked about here, the 2 leading coefficients are 1 and 1. So we're going to divide those 2 leading coefficients. And so that would just be y equals 1. Okay, the x-intercept, we're going to set the numerator equal to 0. The numerator is the top. Once again, they're both one-step equations. If it was a different equation, maybe we could write it out. But in this case, x equals -1, x equals +1 would be the 2 places it crosses the x-axis. So this time there's 2 places. Last one we didn't have any places it crossed the x-axis. And on this one, the y-intercept, you can either plug 0 into the factored form or you can plug it into the normal form, but I think the standard form is a little bit easier, and we've talked about this a little bit before. 0 squared minus 1 is just -1. 0 squared plus 0 minus 6. Really, I'm just going to divide the 2 constants. I'm really just taking -1 divided by -6. It's just the 2 constants at the end, which would become a positive 1/6. Because we have a negative and a negative. So those are like my 4 key things that we're going to use to graph this. Okay, over here to the side, I'm going to graph it. Vertical asymptotes. I always do these with dotted lines because it's not really part of the graph. It's just lines that the graph is approaching. So those are my 2 vertical asymptotes. My horizontal asymptote, I got to go up 1. Y equals 1 is a horizontal line. It's going to cross the x-axis at -1 and +1. And then at positive 1/6, which would be right above the x-axis between 0 and 1. Okay, everything else, we're just going to kind of use our graph now to kind of help us with this. And there's 2 options to put this into the calculator. You could put the factored form in, but probably the original standard form would be a little bit easier. But once again, we want to make sure that we use parentheses here. So as we go to our calculator, and so this one, go here. Then we want to make sure that it goes through all of our intercepts. It's kind of a parabola here in the middle. And then part over here. I mean, if we went to our table of values, there would be points on the graph at each one of those different kind of branches of the graph. So kind of a weird looking graph, right? Because you got graphs all over the place, or parts of the graph all over the place. And all three of those branches are all parts of the graph. In this today. Okay. Let me give you another one here, and this one is a little bit different. They're all a little bit different. X squared minus 4 on top. Bless you. Okay, the bottom's already in factored form, so that's the good news about that, is that it's already been factored out. If it's not, we want to get it factored out. The top is not factored out. So that's kind of like the one we did just a second ago. If we factored out, it would be x plus 2, x minus 2. And then it would be x plus 5, x minus 2. Okay, as we go through all of the different things here. Sometimes it's easy to forget about holes because on the first two examples we didn't have a hole. This is the first time we've actually had a hole. I got an x minus 2 on bottom. I got an x minus 2 on top. Because there's a common factor on top and bottom, then there's going to be a hole at x equals 2. We would set that factor equal to 0, and that would give us x equals 2. I'm kind of skipping the solving part because it's just a one-step equation. Okay, my vertical asymptote then, because this is a hole, we can't use it for the vertical asymptote. So the other two factors that I have left on bottom would be my vertical asymptotes. So that would be x equals 0, because x is all by itself right there. And then x equals negative 5. So it has two vertical asymptotes, it has a hole. Okay, the horizontal asymptote. This one's a little bit harder to come up with because this one's in standard form, this one's in factored form. If I were to multiply all of this together, what would be the degree of the bottom? Yeah, and here's the easiest way to do it. I got an x, I got an x, and I got an x, right? So if I took x times x times x, that would give me x cubed. And you don't actually have to multiply it all out unless you really have a desire to FOIL and do all that. We just need to know what the degree is, right? So I have a degree of 2 on top and a degree of 3 on bottom. And so the top is less than the bottom. And when the top is less than the bottom, if you got to go back and look, you can. Okay, top is less than the bottom. 1 that we're going to see is the x-axis. Okay, the x-intercept. Because this was a hole, then it's not an x-intercept. There's a common factor right here. So the only thing that I'm going to set equal to 0 here would be x plus 2 equals 0, which is x equals negative 2. So it's going to cross the x-axis at negative 2. The y-intercept. This one's a little bit, and you could just get this from your calculator if you wanted to. 0 squared minus 4 is negative 4. 0 times 0 plus 5 times 0 minus 2 would be 0 times 5 times negative 2, but 0 times anything is 0, okay? And so, in this case, what we're finding out is, because we have, when we divide by 0, it's not going to work, then there would be no y-intercept. Because we're dividing by 0 when we plug that in. All right, let's graph this, and then let's talk about all the different things that are going on here that kind of makes this a little bit different. All right, so let's start off with our vertical asymptotes. Okay, and right here, because we said it has a vertical asymptote at x equals 0, this line right here is your x equals 0 line. That's why there's no y-intercept, because my y-axis is an asymptote. Okay, and so your y-axis here is an asymptote, so that means it can't touch or cross that, and that's why there's no y-intercept. Okay, x-intercept is at negative 2. Horizontal asymptote is the y-axis. Now here's the first thing that's going to be weird, okay? And this is something that can happen. It doesn't happen very often, but it can happen. We have a horizontal asymptote of the x-axis, and we're also saying it has an x-intercept, okay? And that doesn't happen very often. But there's a reason why that happens. And I'm going to show you the graph, and I'm going to show you why that happens. Usually the graph is going to approach it and not hit the x-axis. But here it's actually going to cross the x-axis at that point, which is kind of weird. Okay, so let's put... Okay, and then it's kind of a cubic looking graph over here, and then it has this other branch up here. So more than anything, the asymptotes are just there to kind of help us guide where our graph is going to go, and it can't cross those lines. And so drawing those vertical asymptotes in is a pretty big deal as you do a sketch of this graph, so that when you draw your actual graph that it's approaching those lines. We would not want this graph here to like go past it, okay? Same thing here, we don't want this to go past the x-axis or the y-axis. And so that's why drawing those in there is kind of a big deal. All right, questions on any of that? The only other thing that I did not talk about, and there's a few places that they're going to, but you will see some domain questions. All right, assignment for today. Going by fives, and you can skip number 30. Number 30 talks about what we call an oblique asymptote, and we're not going to do any oblique asymptotes, so you can forget about that.